So hello and welcome back to this online machine learning course. In the last few videos, we dealt about machine learning. We classified machine learning into supervised machine learning and unsupervised machine learning. We dealt into supervised machine learning and classified into classification and regression. Now in this video, we will be dealing about something different. So when you deploy a machine learning project or a machine learning module, you would be having a machine learning algorithm or a model over here, and you would be feeding data set to your model, train it, and then store your result in some database or a data container, right? Or somehow pickle your file. And then when we would predict a new data, or we want a new for the model to give you a new output, it would give a result, whether a regression or a classification. And this model can somehow vary. This data set can vary, this training can vary, this pickling can vary, everything can vary. Now, the thing is that apart from logistic and linear regression, there are other powerful algorithms, very powerful algorithms. And the thing is that no matter how powerful your algorithm is, if you do not apply certain feature engineering on your data set, you will not be able to achieve a remarkable accuracy. And feature engineering on data set is somewhat working on your data set, featuring your data set so that your model is able to predict or classify perfectly, or it is able to build a proper decision boundary properly. So today we'll be dealing about a technique known as normalization. So it is a technique often applied as a part of data preparation for machine learning. And the goal of normalization is to change the values of numeric columns in the data set to a common scale without distorting differences in the ranges of values. Now what I mean is that, suppose you have got a column of age in this one, and you perform a salary in this column, and from this you are predicting whether a person qualifies for loan or not, or something other than that. So your age is of the range, generally of the age between 0 to 100. Your salary is of the range from perhaps of course 1 rupee, a very arbitrary salary, to somewhere in billions, considering billionaires and so on. Or okay, so your salary has got this scaling. And now if you go on predicting, since these are of different scales, I somehow divide all of my salary, divide by the billion, 1 billion perhaps, and divide this by 1 billion, divide this by 1 billion, divide this by 1 billion. You can see that all my values are in the range of 0 and 1, right? All my values are in the range of 0 and 1. And so this goal is to bring it to a certain range. In this case, I took the range to be 0 and 1. It could be any n and m, and that is what my basic goal is. Now let me tell you why it is important. So let's, for example, get back to the example we have been dealing so far in previous videos. As you can see out here, let's for example, this x1, x2 till xn are features, and b1, b2 and bn are my weights, and b0 is the bias, and y is a predicted output. Now x1 till xn will have different normalizations, different ranges. Now let me take this example as this is of the range between 0 to 10 to the power 4, and this is in the range of 0 to 10 to the power minus 2. Now, if you do not bring these two in a given range of 0 to 1, or perhaps some other ranges, if you do not scale these features, what you are going to occur is that your weights will have a tendency to bring these into your own features, into their own scalings, and you would somehow, let's for example time being assume that x1 was an important feature than xn, and ideally b1 has to be greater than bn, but since it is bent on scaling up, you somehow lose that intuition that b1 has to be greater than bn. And this is how, because as you can see out here, this is of the order of 10 to the power minus 2, and this is of the order of 10 to the power 3 or 2 perhaps, and so these two we end up getting a wrong classifier and we do not get good classification results. I hope you get the intuition by now. So there are types of normalizations, namely scaling to a range, feature clipping, log scaling, and z-scores. There are various other normalizations. We apply normalization to image data, we apply different normalization to language models, and so on. But in this video, we'll be dealing with only these four. So first of all, we'll be dealing with scaling to a range normalization. So in this part, what we do is that we take any x, subtract it from the x-min from it, and divide it by x-max minus x-min, where x-max is the maximum in this column and x-min is the minimum in this column, right? And by now, it is obvious that x dash always lies in the range of 0 and 1. Right? For all xi's, it always lies in the range of 0 to 1. And there are two conditions where you must use this normalization. The first is when you know what your upper and lower bounds are. In the last example, age would be the perfect case, because you know what your upper and your lower bounds are, because generally the ages are 0 and 100. There may be few exceptions or few outliers, and these outliers may be people above the age of 100 or 110, and they are very few in our case. And the second one is that your data is approximately uniformly distributed across that range. What I mean is that your data must have, for given sets of all the classes, you must have equal number of data points. And age perfectly qualifies for this, because in the age gap of 10 to 20 and 20 to 30, we generally have the same number of people all over the world, or in a given country, or in a given district. And this could be even extended till age 10 to perhaps 10 to 40 and 40 to 70. We generally have the same distribution. Now, the thing is that salary does not advertently qualify for this condition, because people above the range of the salary of 1 million is a very small number. People less than the salary of 10,000 per month is a very large number in a country like India. And there is no upper and lower bounds on your data, because uh, people are at one stage earning around 100 rupees per day, whereas there are people who are earning billions per day, and so there is no upper and lower bound. So salary does not qualify for this scaling to a range normalization. We have feature clipping normalization, which is identical to threshold, wherein you set a threshold and you clip up all the features or all the values above this threshold. As you can see out here, these outliers are dropped to 0. These outliers are dropped to 0. And so it actually clips all values above a certain threshold or a fixed value. We then move on to something known as log scaling. Log scaling is given by this this function, and you may have seen log scaling a lot in the COVID-19 charts, and depending on the countries, you would see the log scale would either be a straight line or a plateau region, depending on the country. I took the case of China, where the graph is currently a plateau one. Maybe in the case of India, it would be a steep right now, and so on. Now basically log scaling is helpful because if you have got large number of data points for one set and a very small number of data points for the other set, you can actually normalize it and perform a data like something like this. And so this is handy when a handful of your values have many points while most other values have few points. As you can see out here, generally all the data points are in a similar range or all have near to equal distributions. Let's move on to something known as Z-score. The Z-score is the most commonly used normalizer. Now, the Z-score is a variation of scaling that represents that the standard deviation is away from the mean, and it is the most commonly used, and we term it as, the formula it is given by x minus nu by sigma, where nu is the mean and sigma is the variance. The nu, now as you can see out here, this x dash or the range of x dashes have exactly 0 mean and unit variance, and so it is indeed one of the reasons why we use Z-scores. The other reason is one in the graph. As you can see out here, you have a range from 5,000 to 45,000, a very large variation and a very large range of values your data set is spread in. If you want to reduce that range and bring it to a smaller range, you can apply Z-score and you can bring it to a very smaller range out here, and these are actually 0.1, 0.2, 0.3 and 0.4, and you can see out here that same graph, the graph before normalization and the graph after normalization are nearly same, only that their scales are much differed, and so our basic goal is achieved. And this is one of the most powerful, works best in most cases. Of course, there are more powerful normalizing techniques, and normalization is based on what your conditions are, what your features are, and that's what normalization is. Now, the reason why I took a long video for a normalization, because it is one of the most important techniques or works which you must do in machine learning. Now, when I started machine learning, even I didn't know the importance of machine learning. Of normalization. I'm sorry. And I participated in something known as Kaggle. It's a very nice platform, and sometime in the near future, I believe we would be releasing videos regarding Kaggle and how to put your first steps in Kaggle. So I was working on a classification problem, and I was applying various algorithms. The algorithm which I was applying was a support vector machine. It is indeed a classifier, and I was feeding my data point and predicting it, and I was getting the accuracy. And initially, I did not do any normalization, and I was getting an accuracy of 0.52, not a very good score. And suddenly, I did a z-score normalization over here. Out of nowhere, I thought of getting a z-score normalization because let's see what happens. And suddenly, keeping everything fixed, my new algorithm was SVM. Everything fixed, my accuracy jumped up to 83%, near to 83%. And so you can see a drastic jump in accuracy over here. And it is after this when I started learning and reading about normalization, and it is indeed a very powerful technique, a nice technique. And if you are dealing with classical machine learning problems, you must perform normalization, otherwise you are never going to achieve a remarkable accuracy, no matter how powerful your algorithm is. And so that's it. Thank you for watching.